Okay, so we are coming almost to the end of this quite a long chapter on ocean circulation. The parts that remain are the thermohaline circulation, which relates to the deep ocean currents, right? We mentioned thermohaline circulation before. Thermo is temperature, haline is salt, so thermohaline. We said there are places where heavy density waters are created, they sink and they set the deep ocean in motion, because the wind forcing doesn't penetrate that deep. Ocean is several kilometers deep, and the wind forcing cannot go all the way down unless it's the Southern Ocean channel where the winds can keep on churning the ocean and can drive Ekman currents to the bottom, right? So deep ocean is what? Basically anything below the pycnocline. The seasonal pycnocline can be as deep as 1 kilometer or a little bit more, and that region below the pycnocline actually holds more than 90% of the water. So the winds are only churning about 10% of the water. But as we said before, the deep ocean moves incredibly slowly, tens of kilometers in a year, so very, very, very slow. Measuring it is very difficult for that reason. So what is the thermohaline circulation then? Basically, we said it is caused by sinking water, high density water, as you can imagine. Probably can be only created at high latitudes, but we will see that there are places like the Red Sea or the Mediterranean where so much evaporation happens that despite the warm temperature you can form some sinking of water in those warm oceans. Okay, so either you can cool it or increase the salinity, right? Often they are related to each other because it's this evaporation which makes cooler waters, and it's evaporation that also adds salt, leaves behind salt in the ocean, right? So the dense surface water sinks, and it sinks so fast that it doesn't mix with the neighboring water. That's critical, because if you are trying to sink a blob of water and it just starts mixing heavily with the water below, then soon it'll become neutrally buoyant, which means it will not sink anymore. So it has to sink so fast that the mixing doesn't happen. This is the same thing in the atmosphere, by the way. We kept talking about convection and so on. That warm air has to rise fast enough to not mix with the dry air around it to maintain its identity as it goes up. So deep water masses are typically identified by these sorts of TS diagrams, which we looked at before. Classical oceanographers like Arnold Gordon will go on a ship and they will just taste the water, and Arnold will tell you where that water came from. Ha ha, I'm just joking, but you can tell Arnold I made this joke. Okay, so this is the temperature salinity diagram. As I said before in another context when we were looking at seawater properties, the relation is nonlinear. It's like a fifth order polynomial, which means the changes in temperature affect the density differently in the warm range and the cold range. Plus, you can take two water masses on the same density line with different salinity and temperature combinations, mix them, and create average temperature and salinity, which will give you a different density than the same density you started with. We called it cabling, C-A-B-B-E-L-I-N-G. Okay, these kind of density-driven currents are important in the ocean. So what's being shown here are the various water masses. They're called water masses of specific density, specific properties, which can be identified because they are maintained for a long time. So Antarctic intermediate water sits here with certain salinity and temperature. Antarctic bottom water. So you can see the densities here, 1.027 versus 1.028. Remember, we're adding salinity and going away from pure water density of 1.0, right, in grams per centimeter cubed. Okay, so Antarctic bottom water is sitting here at 1.028, the heaviest of all water masses in the world. Antarctic intermediate water is lighter. North Atlantic deep water is here, heavier than the Antarctic intermediate water. There is the North Atlantic central surface water, complicated names. Mediterranean intermediate water. We said deep waters forming formation only occurs at high latitudes, but I mentioned Mediterranean and Red Sea can do that as well with high evaporation. And sure enough, you see here Mediterranean intermediate water is a little bit heavier than the Antarctic intermediate water, right? And the North Atlantic central surface water can be as heavy as the Antarctic intermediate water. This is what drives the deep ocean circulation. How does it happen? You can see here the north-south section going through the Atlantic, the red line shown here in this inset panel, and it's showing the depth section with latitude. So there is equator in the middle, north to the left and south to the right. So you're going from here to here. And you can see the various water masses here. You see in the low latitudes you have a well-defined thermocline and pycnocline, and you have warm tropical surface waters, and you have seasonally moving ITCZ, so seasonally changing surface waters. As we go to higher latitudes, when we saw water properties, we saw that it can be mixed thoroughly all the way to the bottom. So you can see that the mixing causes around Greenland the deep water formation, the North Atlantic deep water that forms because of this evaporation of the warm Gulf Stream water that's coming in and the cold atmosphere above. That water sinks and goes south along the western boundary, as we mentioned before. There are details that we won't get into, and crosses the equator and gets into the Southern Ocean. And Antarctica, which is obviously very cold, plus it has these shelf ice which is releasing, is affecting the circulation as well, and sea ice formation. Altogether it's forming the heaviest water we saw as Antarctic bottom water, and it's also forming lighter heavy waters called Antarctic intermediate water that sit above the North Atlantic deep water. If you take a section here and blow it up, you can see that the North Atlantic water is coming in, as we see in this panel, and it's being pulled up. Why? You remember this divergence we had between the east wind drift and the west wind drift, or the Antarctic circumpolar current, and the interior circulation near the coast, right? So you had Coriolis pushing water away and dynamically creating upwelling and pulling up the North Atlantic deep water in the Southern Ocean. Okay, so the Antarctic intermediate water happens to the north of it. So this is the southern pole, Antarctica, and you're going north here in this direction. So you can see the subantarctic zone is 10 to 10 degrees. It's about 4 degrees in latitude. You have 4 degrees centigrade here in the Antarctic convergence zone. In the Antarctic divergence, you have the 0 degrees centigrade waters here, and there is the Antarctic bottom water sinking. Okay, so I'm going to stop this podcast here because you need to look at this carefully and see what are the various water masses and where they are forming. And the Southern Ocean is where they're all coming in, and the Southern Ocean is like a mixing bowl. Water can circulate around several times. The waters get mixed up. 25% of all the deep water in all the oceans see the atmosphere in the Antarctic region, Southern Ocean region, before they disappear for several centuries to several thousands